So we take the square root of both sides. Do I leave it like that? Am I good? What did I forget, obviously? Thanks, Luke. Good. I forget that plus or minus. And if you forgot it at the end of the problem, you're only going to get how many answers? And how many answers do you get from all quadratics? You always get two. Whether they're real, or both imaginary, you always get two answers from quadratics. And then take the 3 and add it over. If the 3 had been x plus 3, or positive, this would be a negative 3 plus or minus root x. Okay, those are my answers, and as Kate said, they are binomial conjugates. They are binomial conjugates. Now, again, to point this out, before I go into the next one, maybe a little more tricky, and we'll go into the quadratic formula of that also. To point it out, imagine instead of a 0 up there, cross off the 0, please, and put a y. Cross off the 0 and put a y. So now instead of looking at an equation, we're going to study a function for a minute. So cross this off, put the variable y there. Now, if I were to determine or try to take this standard form quadratic and move it into vertex form, it would be the same exact technique we just took. Again, this is standard form at the top. If I want to put it into vertex form, I take the exact same approach. Put a y in front of the 10. It's really just y plus 10 over there. So put a y right here and a plus sign right there. There's really a y plus 10 there now. Because now I'm taking this 10 from here and moving it over and then taking the 9 and adding it to both sides. So this would be y plus 19 instead. And this would be vertex form right here. Okay, again, if this were equal to y in standard form and you want to convert to vertex form, this is the approach you take. Now it's in vertex form. Y minus k equals a times x minus h squared. Tristan, go.
Is this easier than the quadratic formula?
To get the answer, you mean at the bottom, not vertex form, obviously. Vertex form, you don't use the quadratic formula.
Oh, sorry.
But to get this, are you asking about?
Yeah.
To get that, it depends on the approach you like. I personally think it is probably easier than going to the quadratic, but it depends on how the problem is given. If it's given with an a value, I'd probably go right to the quadratic formula. If on the test it says solve by the method of completing the square, then you should probably use completing the square, right? So depending on instructions, consider that as well. But for the most part, if you're given a quadratic, it's completely up to you. At a show of hands, how many think the quadratic formula is easier than completing the square? Okay? It looks like about half, maybe 3/4. Some hands are like half up. And that's fine. It does, right? The same thing. 6 and 1/2 does. It's the same thing. Next.
Is there going to be a calculator on the test? Fine.
Allowed calculator? Yes, you are going to be allowed. Yep. I'm going to say the whole thing as of right now because I don't think we had any restrictions on it because it's in like 3 separate rooms and it would be very difficult to do so. There's the only reason we didn't have a part not calculator. Because the honors class is comprised of 20 students from the 2 classes. So you guys I think are like 7 in one room, 7 in another. So, you know what I mean? So to get the calculator functioning and have people have to turn them away and put them down and stuff, I think it was too much. On the AP exam, though, you have half and half. I think maybe even in pre-calc honors, part of the final might be half non-calculator. I'm not sure. But for the freshman course, I'm pretty positive, 99.9% sure that you're not. I actually just ran off the exams yesterday, so I can look at the cover page and remind myself and see. So now, we could also take this idea and just quickly look at the idea, what if the coefficient of x squared had not been a 1? It looks like it's really difficult. I probably wouldn't use completing the square then. Okay, now let's say hypothetically we're a 4. If it were 4x squared. Start by dividing everything by 4, and this is going back to 0 over here. So this is back to 0 on the right-hand side now. Okay, so now let's look at this right here. If I wanted to get rid of a, I divide by 4 in all cases, which gives me a fraction to reduce to. I'm going to get 6 over 4 and 10 over 4 now. I'm obviously going to want to reduce these. And this looks like a complicated problem. It really does because of the nature of it. So if you're at this point and you want to figure out what are the roots of this, it's up to you. But I'd probably go with the quadratic formula. But even there, actually, it could be a little bit tricky to do this with the quadratic formula itself. And so I'd probably stick with the coefficients that I had in the first place. I'm using the quadratic formula. But completing the square-wise, what's half of 3 halves? What's half of 3 halves? Don't give me decimals here. It doesn't make sense to use decimals. 3/4. So how do I know that? Don't say because 0.75 is 3/4.
You multiply it by 1/2.
Yeah, you just take the fraction and multiply by 1/2, which makes it 3/4, right? Or just double the denominator. Guys, pick up on that by now, right? When you want to have something, you double the denominator. So half of this would be 3/4 by doubling the denominator right here. And then 3/4 squared is going to give me 9/16. So I move the 5/2 over. I'm going to have a 9/16 to add to both sides. And this is what I was referring to, so please take a note of this right now. It is not impossible, but it's very difficult to factor this if you're just trying to actually factor it, because in fact it's all fractions. But if you recall that your factors will always be x minus whatever b was cut in half, you can put that in already. So because we said we got 3/4, when we took half of this earlier, it was 3/4, this factor is going to be x minus 3/4. Now what's 5/2? I'm just going to take this and multiply this by 8, making that 16, and making that 40. 40 plus 9 happens to be 49, and that's over 10. 16, sorry. 16. Okay? Yeah, I know. That, I was going to say, what does that infer? This is a great point, actually. This is a great question. By throwing a 4 as a value, suddenly we got something like this. What can you tell me now? Bridge already pointed out that they're both squares. Right? These are both squares. Come on. Kate already made this conjecture before. Somebody else finish up with it. Follow up.
But they're conjugates?
In this case, they're
They're
not conjugates.
not, okay.
Okay? Because earlier, why were they conjugates? Because it wasn't a perfect square, right?
Oh, right.
Now, because they are perfect squares, we're not going to get necessarily binomial conjugates. We'll get just rational answers. Okay? So earlier, we could not take that square root. Exactly. Very good. It was root 19. So take the square root on both sides. Plus or minus 7 over 4. Right? The square root of 49/16 is 7 over 4. Just do it individually. And then tack on the 3/4 rather. You're not going to leave your answer like this, obviously, right? We all know that. If you can simplify, you always simplify. 3/4 and 7/4 is going to give me 10/4, which is really just 5/2. And then 3/4 minus 7/4 is going to be negative 4/4, or just negative 1.
Wait, could you go to the original problem?
The original problem.
Not the problem, yeah. Can't you just multiply the whole thing by 4 into...
Well, we originally started with it. We were just doing this by completing the square. That's the only reason. But yes, absolutely, Tristan. The original was 4x squared minus 6x minus 10. And for that, you probably should have just used the quadratic formula. Okay? Definitely. But what I'm trying to show you is that fractions, non-fractions is the same approach. It doesn't matter whether you have fractions or
We're
not.
not doing fractions, complete the square and the final round.
What did I tell you about everything this year?
Um,
I said yesterday. You're asking a question that you know the answer to already, right? I said anything you've done this year is fair game. You've done this year. We've done completing the square, and we've done it with fractions. So I can't tell you what's on the exam, but you need to know that everything possible from the year is on the exam. I can tell you that it's weighted toward the second semester more, but that's written on your review guide. Okay. Expect to be able to do anything on this. What else? That was completing the square with a little bit of quadratic stuff, right? We did a lot there. That was very useful to look at our answers with whether they're rational or binomial conjugates like we saw with the previous one. What other kind of stuff do you want to get into? Yeah, Annette, go ahead.
Like the division of polynomials, like you'll have...
A fraction over a fraction?
Yeah.
Like-
Or, no, stuff like that.
With like fractions and then fractions in different spots and stuff?
Yeah.
We called it complex fractions? Is that what the one you're looking at? Okay. Yeah.
This one's a little bit of an older topic, but could we do, like, there's a graph of line that goes through 2, 6, and like 3, 1?
Yeah, sure. Equations and graphs of lines. Yeah, we'll get to that next. Linear functions. With what?
When they give you like a very specific information, you have to...
So it needs to be parallel to this line or perpendicular to another line or go through these points or tangent to a circle, something like that? Okay, well, I wouldn't do tangent to a circle. It's geometry more. All right, so let's take a look at a fraction. Now, to make these problems up, you kind of have to use problems that are useful. So I'm going to make sure that they work. So you don't want to just pick arbitrary things for this. It would work still, but it would just be very messy and lengthy. So there's two approaches we can look at. Okay, you can recall that we can make an LCD of the whole thing, or we can look at the fractions individually. So let's look at a problem where the numerator has one fraction in it and the denominator has two. Okay, something like this. Let's say that the numerator's fraction is 2x over x squared plus 5x minus 14. Let's see. Let's make this x plus 7, x minus 1. Make this x, make this 5. Okay, and the question simply says the following. Simplify the fraction as much as possible. Simplify the fraction as much as possible. So when I look at this right away, I think about if I have fractions and I want to combine them, I need to do something with the denominators. Whether I'm going to multiply by the LCD or find an LCD for each part individually, I have to do something with the denominators. That's the important part. When a denominator is given in a polynomial form, what's the first thing you want to think to do?
Factor it out.
Factor it. Okay, for anything, right, guys? Think about it this year. Go back to anything we've done this year. When you have something written as a quadratic and you want to know more about it, usually you factor it, right? Mr. Donachek actually has a saying he talks about with his senior pre-calc class. He jokes with him and says, when in doubt, factor out. Not always, obviously. It's not always factoring. But there's a lot of the time this year that you're going to have to factor things that are written in either quadratic or generally polynomial form. You want to factor it first. So let's start with the numerator here. It's useful to factor my numerator first so I can see what I'm dealing with. So I've got the 2x here. What does it factor into? What have I got there? What have I got, Bridge?
X plus 7, x minus 2.
Very good. And it would have been really nice if it were x plus 7, x minus 1, but it's not. It's x minus 2. Didn't make it that easy on me, you know? If it was the same, then it's like nice and convenient there. So what method do you want to take here? We have option A of multiplying everything by the overall LCD of all the fractions. Option B, find an LCD of the bottom. We have the top already done. And then think about a fraction divided by fraction as multiplication by the reciprocal. Remember, when you divide a fraction by another fraction, it means multiply by the reciprocal. So if we can make the denominator one fraction, that would make it pretty easy on me, right? Or I can multiply everything by the overall LCD of the whole thing, of all fractions. Now, the problem is that if I try to find the LCD of the entire thing, it's x plus 7, x minus 2, x minus 1. It's really just annoying, right? I don't want to have to look at the overall LCD. Then I got to multiply the whole thing here, distribute it out. That makes this problem a little more difficult than it's worth. So instead, what I'm going to do is I'm going to find an LCD of that denominator. What's missing here is x plus 7 and x plus 7. What's missing here is x minus 1 and x minus 1. And remember, when in doubt, just write what's missing that's in the other term. That's always the easiest way to go through this. So because this one has x plus 7, this one needs it. Because this one has x minus 1, this one needs it. So we have to multiply by that over itself. Okay, so the denominator will now become this. We're going to have 5x minus 5 when I distribute the 5, plus x squared plus 7x, all over x minus 1, x plus 7. The numerator is still the same. Okay, so again, take a look. If you're having trouble with this 5 gets distributed. 5x minus 5 comes here. This x gets distributed to become x squared plus 7x. And that comes about here. Now, please, if at this point in the year you're having trouble with this still, write this down right now. You can cancel things that are in the denominator of both denominators, just like if things are in the numerator of both numerators. So if I had here like a 5, it was just 5, and this was just 5, they can go across down, put a 1 and a 1. So the x plus 7s can actually cancel here. You'll see it in a minute if you didn't do it. If you didn't cancel x plus 7 right away, it's okay, because we're now going to multiply by the reciprocal and we'll see it cancel. But you can cancel x plus 7 at this point. If you forgot to, I'll show you in a minute how that shows about, or how that comes about. So what I want to do is look at this right here and just make this one polynomial. So what would this look like if I combine like terms right here? Simply, come on. What is this? Yeah, George, go ahead.
X squared plus 12x, or, minus 5.
Good. So that's what this becomes. So I'm going to put a line through it just so I can see that I'm replacing that. If you're taking a final exam and you have a problem like this, are you going to rewrite this 12 times every time you simplify one little thing? No, you shouldn't, honestly. Do it in a neat, efficient way. But look what I just did here. That's absolutely fine. Replacing it. And now the next line, just go ahead and multiply by the reciprocals. So we've got 2x over, and this is if I forgot to cancel the x plus 7s, times the reciprocal of that now. This x minus 1 goes up here. This x plus 7 goes up here. And then this entire quadratic here goes down to the bottom. Can I factor this? Tell me, please, in pink here. Can that be factored? I don't think so, right? Can anything multiply to 5 and somehow add up to 12? Just think about the logic behind that. It doesn't make sense, right? So we've got x squared plus 12x minus 5. Cancel the x plus 7s. Yielding one solution at the end. Not very simplified, really. Of 2x times x minus 1 all over x minus 2 times x squared plus 12x minus 5. Okay, a rather lengthy problem for a simplification one because of the fact that the denominators are not going to be perfectly factored into one another, right? Again, had there been an x minus 1 up top, it would have made life a lot easier. So we've got some stuff remaining that didn't cancel, but clearly we saw the x plus 7s did cancel. So maybe a hint or something, no? Okay. Tristan, linear functions, right?
Yeah.
All right. Annette, was that useful?
Yes, it was.
Okay.
I just didn't know exactly when I should cancel and I shouldn't. But I realized that I can cancel I didn't know if I could cancel like the denominators as well.
Yeah, and the numerators both would work too. Absolutely. And that's only one method to use there. The other method we went through was multiplying the top and bottom of the major fractions by the overall LCD. That works too, but it wouldn't have been useful in that problem, or it wouldn't have been optimal in that one. Let's say we've got something where we know that one of the points is 2, 7 on the curve. Okay, and let's say that it is perpendicular to y equals, y equals 3/2 x plus 8. We want to find a function that goes through the point P, which is 2, 7, and it's perpendicular to the line y equals 3/2 x plus 8. It's a good question, Tristan. What do you think? What should we start with? Somebody give a first step here. What do you think we want to do right away? George, what do you got?
Just plot the y equals 3/2x plus 8.
Plot it, you said?
Or like draw it on.
You could, but it's not even needed. But George, you could do that if you wanted to, but it's not necessary actually. No graphing is needed here. It might be useful to look at, on a calculator, maybe pull it up real quick, get a look at what it looks like, but it's not necessary. And be careful on the calculator, perpendicular lines don't look perpendicular always in the calculator because of the screen the screen is like stretched this way, right? So they don't always look perpendicular on the calculator actually. What do you think we're going to start with?
Maybe plug in 2, 7 into the equation.
Now, if I put 2, 7 in the equation, it's just going to say, is that an answer to that equation? That doesn't help me really. All right, try putting 2, 7 in. Does it work? I don't know. Maybe it does, maybe it doesn't. But what does that really tell me, right? It only tells me if 2, 7 is on that line. But I don't care if 2, 7 is on that line. I'm putting it on a new line itself we're coming up with. Yeehaw, what do you think?
Oh my god, so like get the negative reciprocal of y.
Of 3/2. So we take the slope of the other line, and because these lines are perpendicular, we can write that the slope of our line is going to be negative 2/3. Again, slopes of lines that are perpendicular are negative reciprocals of one another. This is just a fact. We've proven it. We went through where it comes from. But you need to, at this point, know that fact. What about lines if they were parallel? What do you know about their slopes? If they're parallel, they're the same. And it makes sense so much more there, doesn't it? Because if two lines are following the same slope, they got to have the same rise over run, right? To be literally parallel to each other. Isn't that what parallel lines are? Lines that are parallel have the same rise over run ratio, which is the same slope.
Quadratic parallel lines.
Those would really be considered like concentric circles. You can think of arcs that are concentric, and that's similar in nature to parallel. Think about a bagel. The inner circle and the outer circle of the bagel. technically speaking, if there was a perfect circle, they would share the same center, right? That's concentric, and it's like parallel, right? They follow the same curvature. That's having the same radius of curvature. It's very similar. It's analogous with curves to lines that are parallel. Is that clear what I'm saying? Okay. I wouldn't really go through quadratics and say that, though, because quadratics are a little bit different. But curves that follow constant curvature and have a constant radius of curvature would be considered like parallel lines, like parallel curves. Okay? It's kind of like roadways, right? If you've ever been on a roadway where it turns, the little dashed lines in the lanes, don't they have to run next to each other as they curl like that? That's like constant curvature, is what I would say. It's not a quadratic, though, but it is that same idea, Luke, yeah.
I kind of think like train tracks, too. 'Cause
Yeah.
They go together.
Absolutely. Train tracks are a perfect example, yeah. Yep, that's a great example. So the lines, for the most part, sometimes they curve. So we've got the slope that we're going to use. We know that it goes to the point 27. Tell me, people, how many ways can I come about this next, or can I go about this next part to come up with the equation of the line? How many ways? What's the answer, Hannah? 3 ways. Thank you, Hannah. And that's 3 ways you know of. There's actually more than 3 ways, by the way. But 3 ways that we're going to go over. 1, y equals mx plus b. 2, ax plus by equals c. 3, y minus y1 equals m times the quantity x minus x1. All of which will give me the same answer. It doesn't matter which way you choose. If you remember that in standard form the slope is negative a over b, then look, you got your a and b value right there from the slope. If you want to just plug in a point slope, because you have a point, you have the slope, and it makes sense to do that, I agree. If you like y equals mx plus b, and you plug in the slope, and then use that point to find b, it's the same thing. Whichever way you want to approach it now is fine. Okay, so let's start with y equals mx plus b real quick. If I had that, I can go ahead and plug in the slope. I could say to myself, I've got a 0.27, let me plug it in. And then I would solve this value for b. Giving me y equals negative 2/3 x. What is b going to become here? It's going to be negative 4/3 added on to 7. That's 1 1/3, 8 1/3. Agreed? 8 1/3, approximately. No?
Oh, yeah.
Oh, you plugged the 2.
What I did was I took this, made this is really negative 4/3 right here. And 4/3 is 1 1/3. So if I add 1 1/3 over to 7, I'm going to get, I think, 8 1/3. So that's what I get from y equals mx plus b. If I use y minus y1 equals m times x minus x1, point slope, right? I can plug in the point in the slope, plug in the point, y minus 7. The other point is going to be x minus 2. And then the slope is going to be negative 2/3. Technically, I'm done. That's all I need. I don't have to go further. These are both right. But if it's a multiple choice, it matters how the answer is presented, right? So if it's a multiple choice and it's given in point slope, you can stop right here. If it's given in slope intercept, you probably want to use this. Or you can do it in point slope, and then you can actually show that these are the same by simply distributing the negative 2/3 and then summing by adding the 7 over the right-hand side. You get the exact same answer. Okay, those are literally the exact same thing. The third method, which is not the one that most people choose, this is the one usually ignored. It's probably one of the easiest, though. If you recall that negative a over b is the slope of a line in standard form, then a is 2 and b is 3. Again, we go through this. Negative a over b is always the slope. And this is negative a over b. So a is 2 and b is 3, really. I can start with that. How do I find out what c is, though? I got to figure out what c is. Not needed. Hannah?
Plug in the point.
Plug in the point. The 0.27, has it been used yet? We didn't use this yet, right? Remember, guys, remember. You got to use the point, you got to use the slope in all 3 methods. Here, we use the slope first, then plug in the point to get b. Here, we use the slope first, then we're going to plug in the point for x and y to get c. These are very similar in nature to one another. Okay, the first and the third method. The second one is the only one where you plug in the slope and the point kind of at the same time and you don't have to do any more. The others you have to solve for the unknown every time. So 2 times 2 plus 3 times 7 equals c. 3 times 7 is 21. 21 plus 4 is 25. And I'm done. And if you don't agree or don't believe if you don't believe that the slope and the intercept are right, who remembers what's the y-intercept in standard form? Got it?
C.
Over?
N. B.
B. C over B. Remember, here's how you remember. If the other one's negative A over B, this is just positive C over B. They're both over B. And this is something you don't have to memorize, but C over B. 25 over 3. Isn't that 8 in the third? Blow your mind, right? Unless you remember this when you're in the year, obviously. 25 divided by 3 is really 8 in a third. So if you had known, you can see the y-intercept from that, and the slope is going to be negative A over B, negative 2/3, and there it is. If I'm giving you, okay, ready? If I'm giving you a problem that has an application, which of these three forms do you think it will come in? Word problem. A cell phone bill costs this much money per month plus this much per data. Find a linear function that represents that, blah, blah, blah. Is it going to be form A, form B, or form C? Which way would it be given and that makes sense? Or which way do you think you'll have to choose? Choose which multiple choice answer represents the given statement above. And you've given a statement about a cell phone plan, you have to come up with a linear function. Is it going to look like A? Is it going to look like B? Is it going to look like C? Come on, people. You should know this instantly. There's one of these that makes sense with the application of the problem, and the other two don't. I'm giving you that the cell phone bill costs you $50 every month flat, but it costs you $10 per gigabyte. Which of these three? I should see every hand at this point. Somebody, don't give the answer, but explain what I'm giving to you by saying $50 a month and $10 per gig.
Well, you're saying $50 a month would be the slope.
$50 a month is not the slope.
Not the slope. It's
$50 flat fee is the
Oh, that's it's the intercept.
good, and then the gigabyte rate is the
Slope.
The slope.
I mixed them.
because I said 50 per month, which makes it sound like a slope, right? But if you're looking at the cost per month, it would be 50 per month is the B value, automatically 50, and then for every gig you use, you have to multiply that by however much it costs, $10 per gig. So it would be 10x plus 50. So for linear functions that are application-based, you're always in slope-intercept form. Always. You're not going to be given in point slope or in standard form. It just doesn't make sense. Does that make sense what I'm saying to you? Why would I give you standard form as choices when the problem is given where it really outlines what the slope and the y-intercept is in the word problem? That's the form you're going to be given. Okay? George? No? Okay. What else? That's a good overview of linear functions. Does that help, Tristan? Those three forms we went through, the type of question?
So form A would be the right form for that.
For an application-based problem, you want to think about slope and intercept because those are the things that are given in the application. Your time, guys. What do you think next? What do you think next? Parabolas? What about them? We have a lot of parabolas. Just give me a little more. What do you want to do? Graphing? Okay, let's do that. I'm just going to give you one that has a nice y-intercept that we can use nicely. All right, here we go. Roots. Somebody wrote in the margin of this book, you don't have to always smile to be happy.
That's really, really depressing.
It's deep. It just means that person isn't necessarily smiling, but maybe they're a happy person.
Well, that's true.
It could be actually not depressing at all. It could be uplifting. In the margin of the book, yeah. Hey, you gotta be nice to people. Some people have tougher lives than you. Keep that in mind, right? Always be nice to people. They could have it rough and you have no idea.
That's really depressing.
All right, let's take a look at another one of these that we're going to graph. All right, g of x equals 2x squared minus 12x plus 18. If you're graphing this function, what do you start by doing? Graphing any quadratic that's in standard form, what do you think you probably want to do first?
Find the vertex.
Yeah, find the vertex, the axis symmetry, that kind of stuff. We'll get to the roots too. So what do I have first? How do I get the vertex? Do I want to do completing the square, honestly? No, it's a lot of work. I don't want to complete the square to find the vertex. How do I find the vertex? You get the axis of symmetry first. That's not good. So we start with x equals negative b over 2a. This is our standard formula we use for the axis of symmetry. Negative b would be negative 12. You right there? You okay?
Yeah.
All right. Sliding around. It's your birthday. You can do whatever you want, you know? You got 24 over 4 in this case, which will give us 6. Now, graphically, I need you to start painting a picture in your mind of what you see here. So if I'm doing this and keeping track on the side graphically, I'm already picturing, all right, here's 5. Let's call that a 5. Let's call this negative 5. So I'm all the way at 6 over here.
Wait, is this now?
Yes.
You guys, which is 3,
Say again?
isn't it? This is 2. It's 12 over 4.
Sorry. I don't know why I'm doubling things. Jeez. Max. My bad. Thanks, Max. Now, after we get the actual axis, we can take that value. Now, what Max says makes so much sense. We want to find this first. Can somebody explain why that is? Why do we find the axis of symmetry before getting the vertex? Physically on the graph, why do we do it? Kate, what do you think?
Middle of everything.
It's the middle of everything, okay? So where would the vertex be, Kate? Somewhere on this line. That's the key. The vertex always lies somewhere on here because this is your symmetry point. Whether it opens up or down, we'll figure out in a minute. So take that value of 3 and plug it back into the original function to get the y value. So let's do g of 3 now. So again, whatever you have there, take that and plug it back in. What am I going to get?
0.
18. Am I going to get 0? Yeah? 18 minus 36 plus 18. It is going to be 0. Son of a gun. Okay, you know what? Hey, that's all right. That's all right. We'll make it work. So let's put our vertex right there. There it is. That was completely arbitrary. We just came up with this example. I think it's going to work out that way.
Your axis of symmetry, I'm sorry.
Yeah, no,
Your
man.
axis of symmetry is always like that, whatever axis, right?
Correct. Always. And then the coordinate is the axis comma y. So the vertex itself, in this case, would be 3 comma 0, whatever you get when you plug in to the actual function. Why do I say that? I was like, oh man, it's going to be one of those problems. What's going to happen now with this problem? Figure it out. Come on. If the vertex is on the x-axis, George, is a double root. Well done, George. Either this graph is opening up or it's opening down. So this is kind of a problem. I'm technically done at this point. I might want another point or two, but I'm done. Because my roots, is it worth finding the roots here? What are the roots going to be? 3, 0. If I factor this original, I take out a 2, and then it's going to factor in a 2, quantity x minus 3, quantity x minus 3. I know the factors already because I have a double root. Now, because the a value is positive, the graph is considered to be what? What's the phrase we use? When a is positive, the graph is concave up. So it opens up. Now, if I want to have some value, look at the y-intercept. What's the y-intercept here? 18. Should be instinctual, right? The y-intercept is right there. It's the c value. Set x to 0. All you get is really cover this up. Here's your y-intercept. So at least I know that if this is 10 and this is 20, I can put the y-intercept somewhere here. And what else can I do? Max, you're on. Go ahead.
You can mirror it, so it's over 3, so it's 6 comma 18.
Well done. There's the other point right there. Okay, because of symmetry, I can mirror it over that axis and come up with what it would be on the other side. What is this coordinate exactly?
6 comma 18.
6 comma 18. This is 0, 18. Then we go 3 units over to the axis. Another 3 units over brings me to 6 comma 18.
And those are all the points in the equation.
For this kind of a graph, because there's no x-intercepts, other points aren't going to help too much. So I can draw my parabola if I want to through those points. Okay, I know it's a double root because the factor x minus 3 would show up twice, indicating a double root. What do I call that? A point of what? Good. Tangent point or point of tangency. Very good. Tomorrow, please come prepared with more questions. It's up to you guys to ask what you want to go over here. Please feel free to look at the review guide also that's on Moodle.